Hello, and this is the lecture for neural network training, and we will cover the topic of training of the neural network model. So let's get started. These are the topics that we will go over. Training overview, we will talk about the chain rule, gradient descent, and we will address the training algorithm, backpropagation, and the convergence issue as well. To start with, let's remind ourselves where the training take place in any let's see if I can use my pen here. In any supervised system, we need to do a training. So basically, we start with the data, okay, with a set of data, and the data will be split into training data and testing data. The training data, we sort of pair them with input data and output, okay, the input data and the expected output, and then what we do, we feed this input data to our model, which is right here. This is our model. What we have here is a function f, which computes the estimated output y, and a bunch of parameters. And those parameters typically are the weights, the biases inside the neural network. So we produce an output, which is y hat here. It's an estimated output by the model. Then we compare what we should be getting, the ground truth or the expected result, with what we got from the model, the estimated, and obviously there will be differences. So we compute error. We feed this error into a loss function, and this loss function basically becomes the main target of our optimization in the training. Basically, the training should minimize the loss function. And based on this minimization, in such a way or in such a manner, we update the parameters to minimize the loss, and then we repeat the process again. We feed in the training pairs, generate estimated output, generate error, feed the error to loss function, update the parameters. We continue this process, and this is what we refer to as training, or more accurately, supervised training. And supervised training, because this concept of training really fits under supervised learning. This supervised training is part of supervised learning. Once we are satisfied with the minimizing of the loss function, then the final parameters plus the function are fed into the other phase, or used in the other phase, which is the online inference. Now I use the testing data to try to get the output and estimated output as well, obviously. So the training basically is really the main purpose is to find the optimum values of the parameters, which provide for me the minimum loss function L right here. Now, there are steps in the training, and we will go over those steps again and again, but roughly the very first step in this training process is this, what we call the inference, or the forward propagation, or the forward pass. This will allow me to compute the estimated value or estimated output for the input. Then we compute the error, which is basically the difference between the estimated output and the expected results. And from that, we feed it into a loss function. We have to define what is the loss function. Now, updating the parameter is basically the part that will take quite a bit of the effort, because updating the parameter, the new value will be the present value of the parameter plus an update. Okay, so what's the update? Well, the update, it turns out it has a little bit of math into it, and we'll see that we have techniques that simplifies that. It is really the derivative of the loss function with respect to the parameters, all right? But it turned out the derivative of the loss function with respect to the parameters is equal to the derivative of the loss function with respect to the function, the derivative multiplied by the derivative of the function with respect to the parameters. Now, because this is really not easy to achieve, so we'll study techniques, the backpropagation, which uses the chain rule, and the gradient descent method. All of those will help us to calculate this update value here, right here, because it's really the key ingredient here, which is how we update the parameters and we achieve to the optimum values of those parameters. Okay. All right. See if you can get okay. Now, one of the things we need to learn in this training for parameters, we need to learn or let's say remind ourselves of the chain rule that we studied years earlier in math. And basically, let's get some pen here. Okay. Basically, it is how to derive a variable. Okay, so let's take an example function here. So I have a function z here, expressed in terms of the variable y here. Then I have the variable y right here. It turned out it is a function of x. Okay, and this is the value of y. So really, you can see that here. Z is dependent on y, and y is dependent on x. The interesting thing what happens is that if we try to define or compute the derivative of z with respect to x, well, it turned out if we use the chain rule, it says that, well, to achieve that, what you do, you compute the derivative of z with respect to y using this equation. We will derive this equation, and then multiply it by the derivative of y with respect to x using this equation. And with this is really the chain rule. Okay, so in the above example, what we do is that the derivative. Let's compute this. So the derivative of z with respect to y is, you can see this equation is 5. This 5 comes from here, 5e to the power 5y, multiplied by the derivative of y with respect to x. And here you can see it's easy to find out that the derivative is 2x plus 2. So now this becomes my derivative. Now you can clean this up by substituting the value of x or substituting the function y in terms of x, and you get here the final equation for the derivative of z with respect to x. Again, here is the secret sauce. Basically, the dz or derivative of z with respect to x, we have an available function which express z in terms of y, so we use that function, so dz over dy, and then I have an equation which expresses y in terms of x, and I derive that equation and I multiply it with the previous derivative, and this will be dy over dx. This chaining here is what is known as the chain rule. Okay. And in general, you can generalize this as dx dz over dx. That could be equal to dz over dy times dy over dt times dt over dw times dw over dx, and you can continue with it. All this is the chain rule, and in this case we are just simplifying computing the expression using this chain of derivatives. Okay, here's another example here. You can see here fx is this expression here. All right, so the chain rule says that first we derive this whole thing, and if we do the derivative, obviously you have this minus 7 multiplied by the same whatever this thing is, and we decrease the exponent. Then we derive what's inside that square here, which is if we derive it, this becomes 3x squared plus 4x plus 2x to the minus 3. So you can see the chain rule, we multiplied, here is the multiplication here. So we started with a black box here, and then we looked what's inside the black box using the chain rule, and we derived it. Another example here for this sub-expression. So if I want to derive this sub-expression, so I'll start with this sub-expression here. So this is the 3, and whatever inside here, I put it here with it, obviously decreasing the exponent from 3 to 2. And then I start looking what's inside the box here, and I derive it. So you can see minus x3 and this derivative of expression up here. Again, I use the chain rule to derive this. This is the 5 here, okay, and whatever inside this box here, I put it, which is right here. Then I derive what's inside the box here, 15x squared minus 7. You can really go over certain examples for this, but obviously the chain rule really simplifies the purpose of it. It simplifies finding the derivative, the expressions for the derivative values. Now, how do we determine the optimum value for the model parameters? As we can see in our the purpose here is to have the optimum value here. How do we do that? Okay, this is part of the training. Well, we do this with 3 methods. Okay, one of the 3 methods. One is to evaluate the loss function across wide range of parameter values. So, for example, let's say you have 2 parameters, A and B. Okay, we evaluate the loss function across A and B. We will see that this is not practical, but it's one method. Another method, compute the derivatives for the least square. I'm sorry, for the loss function of the square errors. Okay, the sum of the square errors, and we'll see that this derivative will set this derivative to 0 and solve the equations. Again, we will see that this is not practical. Okay, and both of these methods are used whenever your model is simple, 1 or 2 parameters. But if you have models with thousands of parameters, these 2 methods are completely not practical. The final method is gradient descent, which uses backpropagation, and this is what everybody does and uses to train neural networks. Okay. So we'll go over an example using simple linear regression to see how training is being done. Assume that I have a linear regression model, and in the linear regression model we know that we're trying to fit a line, and here are my parameters: the slope and the intercept. Okay, so obviously if I want to find the best fitting line, I need to optimize these parameters to minimize the loss function. What we did previously in the previous lecture, that we defined the loss function as the sum of the squared errors. So basically here, when I am estimating a line, obviously the line is not passing by every point, so this is an error here, okay, for this point, and an error for this point, and an error for this point, etc. So when I sum the square of these errors, I create the loss function. And the perfect or the optimum A and B, those values A and B, are those values that minimizes the loss function. Okay, all right. So one method here to find out the optimum A and B, okay, is to plot different values of A and B and generate a plot for the end. Because right here what we did, we have an expression here for the loss function. So you can see that this expression, basically I expressed the loss function as a function of A and B. So I can just vary those A and B's and create this plot. Obviously I want to find the minimum value of the loss function, right? And when I look at it, I find the value of A is 2 and B is 4/3. Clearly, this is a method that depends on plotting the values, looking where the minimum, sometimes visually. And clearly you can tell that this method will not be practical if you have, let's say, thousands of parameters. But it's still a method if you want to want to use it for a small number of parameters. Another way to find out the optimum value of A and B is to derive the loss function with respect to A and set it to 0. And to derive the loss function with this, because you see the loss function is a function of A and B, and we saw this expression which is right here. Oops, sorry. This is the expression for the loss function right here. Okay, all right. So and again, how did we do it? We summed those errors. We summed those errors. We found out every error, we squared it, and we summed all those errors. Okay. So now I take this function, derive it with respect to A, set it to 0, and if you do that, you get something like this equation. And again, you derive it with respect to B, the intercept, and set it to 0, you get another equation. And what we do, we have two variables, A and B, and two equations, and I can solve for A and B. Again, same issue with this method as the plotting method or as the evaluating method, that you can really use this for a small number of parameters. But once you start having hundreds and thousands of parameters, clearly this is not the perfect method for the optimization problem in our hand. Okay, so what do we do then? Well, practically speaking, we use something called gradient descent. And the gradient descent, let's do a definition here. What's a gradient? A gradient at any point is a vector pointing to the direction of the steepest ascent. So for example, here, look at this point here, this vector which points to the summit here, to upward vector, this is called gradient. So which turned out to be the slope of the function at that point. If I have a function of two or more variable, like for example, I have weights like W1, W2, and da. So now I have to derive this with function with respect of more than one variable. So the derivative of two or more variables typically refer to it as a gradient. So for instance, we in the previous slide we computed a gradient. Okay, this is a gradient when you compute the derivative with respect to more than one variable. The gradient method is used to descend to the lowest point. So if you imagine here that we were trying to go to the lowest point here, we're trying to find out the slope and go downwards, because downwards is where the minimum point for the loss function. I think I have a better graph here. So if you think about here, you can see that here the gradient descent is an algorithm of finding local minimum, okay, of a differentiable equation. And imagine this is where we want to, because this is really, if we do a plot here, this is my loss function, and I want to be here. I want to go to the bottom. And if you have, let's say, for example, a ball here, and you can see this ball will take this path here, okay, and this is exactly our optimization algorithm. It will be like a blind person or a ball that is descending all the way to the lowest point, and that momentum that pushes it to descend is the gradient descent algorithm and the backpropagation method that we use. We are pushing this ball downwards all the way to get to the bottom here, okay, because this is the minimum. This is where you have minimum value of L. Okay. Now, so how does this gradient descent algorithm work? Well, typically what we do, we pick random values for the parameters. So in the case of my example, which is linear regression, let me pick different colors here. Okay. We have two variables, or two parameters, sorry, A and B. So we pick two random values. Then we compute obviously we have the loss function. We derive the loss function with respect to A, and that gives me the slope for A, and we derive the loss function with respect to B, and that gives me the slope for B. And then what we do, we compute once we compute those. I'm sorry, I should say not derive. I should say compute, because in this method those derivatives are computed. Okay, we compute those slopes, and then I update the parameter, which is either A or B, based on the old value minus the step size. What is the step size? Well, the step size is really the slope, which is coming from these equations, okay, multiplied by a learning rate, which is typically between 0.5 and 0.01. Now, obviously, this is repeated. Okay, so every time I have to, we start with, we compute these slopes, we update the parameters, and then we repeat again. We get errors. We compute those slopes and gradients, and compute the updates and repeat again. We do this until when? Well, the convergence criteria is that until we go beyond a certain level of a loss value, the loss function. Say, suppose you want the loss function to be less than 10, for example, or the step, which is right here, okay, becomes less than a value, okay, or you repeat this, let's say 1,000 times, okay. So these are all criteria of convergence. Okay, So now let's see. So we go back to our example, which is the line fitting example. We started with A and B random value as 1 and 1. We evaluated the loss function. Well, it turned out that the loss function, which is right here, by the way, okay, I forgot to mention we started with A and B equal 1. We chose learning rate 0.01. So the step size will be slope times 0.01. Okay, so this is in the update equation. So the sum of a square error is my loss function, which is right here. If I derive it with respect to A, it is this function here. This is what I will compute every cycle. Okay, so this is the slope for A, and this is the slope for B. Okay, all right. Now, so now I compute the slope for A and slope for B, and then using these slopes, I can use this equation to update the values of A and B and generate the value of A and B. Then what? Then use these values now of A and B, go through another iteration. Okay, you can see these are the new values A and B, and compute the loss function. Notice the loss function dropped from 44 to 5.312 because those A and B's are better now, but not perfect yet. We plug in the A's and B's in these equations for the slopes. We compute the slope, which is right here, okay, and we compute the slope here using these equations, again using these equations on top. All right, okay, and then from these slopes, again, I compute step size and I update the variables A and B, or the parameters A and B with the new values. Then take those new values and repeat again, another iteration, okay? And you can see that the loss function, every iteration is dropping. From previous using previous method, I know that A, the perfect value is 2, and B, the perfect value or the optimum value is 4/3. Notice after I run this algorithm, I am approaching the optimum value for A and the optimum value for B after 100 iteration. After 200 iterations, right? You can see the A is getting very close to 2 and the B is getting very close to 4/3. Now the question here, obviously, the 100 iteration, 200. Can I speed the process by changing this learning rate from 0.01 to 0.0? Let's say in this example 0.02, and the answer is yes. We can expedite the learning by changing the learning, making it higher. But here's the trick. While we are getting really quicker to A and B, after 200 iteration, we are getting perfect A and B. Okay, if you increase more the learning rate to 0.05, then you will get garbage here. And here is the conclusion. The learning rate, there is a sweet spot. There is value that can help you and speed up your convergence. And if you use large values, and 0.05 seems to be large for this algorithm, for this example, then you might end up into cases where you cannot converge here. So there is no convergence here. Okay, so it's a very delicate balance. And typically, my advice here is that use a small learning rate, and then if it works, gradually warm up to larger values. Okay. So, learning rate, we should use the highest value that speed our convergence, but at the same time the model is stable. Okay, in this case, the model start to give me erroneous results. Okay. So now we return back to our training algorithm and we say, all right, so what do we want our training algorithm to do? Well, it computes the optimum value for the parameters. We know that. Backpropagation technique, we will use it to update the parameters. See, now we start to hearing, we are introducing the word backpropagation. See, in the example that I gave you here, what we did, we calculated their equations. All right. Let's see if I can go back here. You see these equations right here? These equations, we calculated those equations. We calculated the derivative of these equations. For large models, these equations become very, very complex. We don't want to be calculating those. So backpropagation method, what it does is it makes the calculation of the derivatives easier without going through complicated, messy derivative equations. So we just update the parameters by propagating the error from the output to the input layer. Okay, and we will see that how. Again, we remind ourselves with the main steps of the training. We compute the loss function for each parameter. We find this the derivative of the loss function with respect of p. We update the parameters. This is the new value, the old plus the update. The update equal the derivative with respect of the loss with respect to parameters times the learning rate. Okay, typically we use the chain rule to compute delta L over delta P, where P is the parameters here. Now, a key point of all of this is this loss function. So far, what we have done here is that we have used this loss function as the sum of square errors, which we used in the fitting a line in linear regression. But some of the authors in machine learning, they like to use the mean square error, which is to, if you have k points, you divide the loss function by k. That takes it from sum of square errors to mean of square errors. So this is more used in machine learning. Okay, and my take on this is, in terms of optimization, it really doesn't matter. The math and derivatives for both the same, except for the 1k factor here. Okay, so this one has this 1k factor extra. However, the loss expressed as a mean square error normalizes the results, which is typically very useful when you normalize the results. So from now on, we will shift our definition of loss function from sum of square errors to mean of square errors. Again, the difference, both equation is adding the errors. So these are errors, AI, where the error is the expected minus the estimated. Okay, so they sum their squares, right? They sum their squares, and same for here. But this equation, it uses this 1 over k for normalization. Okay. Now, a key thing in backpropagation algorithm is this delta L over delta P, where L is what? My loss function. And the P are the parameters, A, B, the weights, the biases, etc. And now it is important to compute this delta L over delta P. And it turned out we can use the chain rule to simplify the computation. First, we can compute this delta L with respect to the F. Then we can compute, because notice this L is expressed in terms of F here. Then we can derive F with respect to p, that makes computing this derivative a lot easier. Okay, now how can I compute delta L with respect to f? Well, this is the equation here, so you can see I have a square root that comes in here, 1 over k that comes in here is 1 over k, and then the f has a minus here, and this is the minus here. So this is the derivative of delta L with respect to f. And now I can use this. You can see this is very easy here, because we are just subtracting the expected minus the estimated, and we are summing them, and we multiply the derivative of the function with respect to the parameters. That will give me the change or the derivative of L with respect to parameters. Notice this is right here is what I need to compute. I'm computing these delta L over delta P, because this is what I use in the update function. Let me just remind ourselves here with the equation here. Notice that I use this in the update. See this update right here? It uses delta L over delta P. Okay, that's why I'm after this. How much change I need to do in my parameters when the L changes, or when there is an error, because I need to fine-tune. This is what tells me how to fine-tune the parameters. Okay, and that's why I'm going through this exercise of finding delta L over delta P, because this is what will help me fine-tune the parameters. Okay. Now, it turned out this is very simple. Anytime I can, this is basically my error for every, by subtracting the expected minus the estimated, this is my error. But this turns out to be the harder part, and that's why I use the backpropagation to compute delta F over delta P. So the change or the derivative of the output of the model with respect to the models. We'll see that this minus 2k, we'll ignore it for now. We'll add it at the end, because sometimes they confuse us. So we'll put this term aside, and we will add it later on at the end. Okay. See here in the linear regression here. Let me look at this plot here. I forgot to mention something. Notice that here how the expected minus the estimated, expected minus estimated, expected minus estimated. So this is the first error, this is the second error, this is the third error. Okay, all right. So if you look at the loss function, if I express it, it will be what? It will be 1 over 3, right? The first error square plus the second error square plus the third error square. Okay, that's basically my loss function here. Okay. All right. Now, again, back to the training algorithm. We will see that in the training algorithm, now notice that we've gone through this algorithm multiple times, and every time we fine-tune it. For each data point, okay, of what? Of the training data, okay? We have xi and yi. We go through forward propagation or inference and compute fi. Then we compute the error, which is ei here, okay, which is the difference between the expected minus the observed. And then we go through backpropagation to compute the delta L over the delta P for every parameter. Notice the I refers to the date to the input, to the input I of the training data, and the J refers to the parameter, to the J's parameter, parameter, okay, in this notation right here. Okay, so now I go through the backpropagation to compute those. This is the difficult part, folks. This is the difficult part, and this is where the training algorithm spend quite a bit of computation. Now, for every parameter, now what I do, I sum all these derivatives across the inputs. All right. So suppose I have two inputs, and every input give me different value here. I sum them up to find the delta L for the delta P for each parameter, and then I do update. Use this one here, multiplied by 2k by the learning rate. I get the update value. So now the parameter, the new value, equals the old value plus the update. Okay, I want to just always remind ourselves that to do the update for parameters, okay, this is how I fine-tune the parameters. Okay, I need to compute the update, and to compute the update, right, I need to compute delta L over Pj. J is every parameter, delta L over delta P. Okay, and to compute that, I need to do what? Backpropagation. Okay, so you see how this, why we are doing backpropagation? Well, to compute the update value so that I can fine-tune my parameters. Okay. All right, so in the next slides here, we will go through the backpropagation and parameter update, and I'm looking at my clock here, so why don't we stop here, and this would be a good stopping point, and we pick up the rest of the lecture in the next video. Thank you very much.